So our next speaker is Gregory Falkovich from the Weizmann
Wine and beer, right? Wine and beer.
And his more specific title is Broken and Emerging Symmetries of Turbulent State.
Thank you, and thanks for inviting me. I'm a physicist, and 25 years ago, I guess, at Bursorovet, I met Dennis, and he told me things which I remember ever since. He told that you physicists do not deserve Navier-Stokes equation, which is, I mean, the longer I work on.
What did I say? What?
You say that we physicists do not deserve Navier-Stokes equation because we don't understand what kind of a precious thing we have, how beautiful it is, anyway, so.
Love story.
And it's true, but at least we have a good sense that from time to time, as you know, people who get gifts which you don't deserve, we bring it to people who probably more deserve. So what today's talk is that I'll tell, there will be no theorem, there will be practically no definition. It will be very empirical statement about things that we observe, or we compute them just solving numerically partial differential equation, or we measure it in the lab, or we measure it in the environment. So there will be facts, and as facts, there will be statements made with a finite precision. It's a measurements, right? So they have a finite accuracy, and to some extent they answer yes, no question, but to some extent. But I think that these two groups of facts, empirical facts, which more or less related to symmetries of turbulence, deserve interest of mathematician. And so let me first, we generally define turbulence as a kind of a farthest from equilibrium state, so that as you kind of pump system farther and farther away from equilibrium, and the system could be anything. But quintessentially, it all started from just pumping fluids. So if you imagine that a fluid has a diffusion in it, and this diffusivity, it's a diffusivity of momentum, and as any diffusivity, it has a dimensionality centimeter squared per second, and it's called nu, and it's something which characterizes the diffusion, and so the motion of a fluid can be characterized by a dimensionless number. So you take any, whatever is your velocity, could be, you know, this velocity of this rotation on this scale times your size, you divide it by nu, it's called Reynolds number. And what we're talking is about this Reynolds number, very, very large.
It's a pure number.
It's a pure number, it's a dimensionless number, and any cloud above your head is 10 to 8. 10 to 8.
10 to the 8.
10 to the 8,
cloud
yeah. The cloud above your head, not large cloud, it's just kind of a moderate cloud. A pipe, when we take a gas and we pipe it from one country to another, we usually burn about from third to fifth to half of this gas just to physically move it. And of course, this friction, which is we need to overcome, is because of this viscosity. But as Camilla told you yesterday, it stopped depending on viscosity when this Reynolds number passes something like 10 to 5. So usually pipe flows are 10 to 6, 10 to 7. And it's not $1 billion question, it's $1 trillion question.
What do you mean?
When your Reynolds number are getting larger than 10 to 6, it stops depending on viscosity.
Oh.
Which means that summer or winter, viscosity changes by tens of percent.
Oh, you mean the cost?
But the cost is a work that you need to do. To push the gas, you need to burn the gas. So we burned a lot of gas just to push a gas from place to place. And that was anomaly, which was yesterday, Camilla told, anomaly in the following sense. It's more or less maybe in the sense of Nati Zyberg, as we defined anomaly, that you have something which is a mechanism, a diffusion. It breaks the symmetry. The symmetry which it breaks, it's time reversibility. The moment you have diffusion, you have dissipation. You have diffusion, you break time reversibility. Then the symmetry breaking factor goes to 0, nu goes to 0. But the effect of symmetry breaking, now how much work you need to do, stays finite. So it does not disappear in this limit when viscosity goes to +0, as mathematicians would say. Okay, and today I'll talk a little bit more about anomalies which appear on the next level of different symmetries of turbulent state. So let's say that I'm trying to, because it's a highly fluctuating flow, I would try to describe it statistically. So I take, say, 2 points and measure velocity difference between these 2 points. So this moves this way, this moves that way, so there is some velocity difference. It's a vector. I can project it on the distance between 2 points, take a longitudinal velocity difference. It would make it a scalar. Now it depends on these 2 points. I assume that it's translational invariant, namely I am deep inside a big turbulent cloud, and so it does not matter whether it's here or here, so it would only depend on the distance between these 2 points. I also assume that it's isotropic, that my turbulence is isotropic, so it's kind of a function of 2 scalar variables eventually. Okay, so it goes down from a function of 2 vector variables to a function of 2 scalar variables. Okay? One scalar is the velocity difference projection on the longitudinal, the direction from point to point, and another just a modulus of a distance between these 2 points. Okay? So I'm interested in this probability distribution, and in particularly I'm asking what kind of symmetries this distribution has. For example, I may ask if it has time reversibility. If it has time reversibility, that it means that only even moments of V could be non-zero, because any odd moment of V would break time reversibility. I may ask whether it's also scale invariant, namely, if it's not a function of 2 variables, but it's a function of a single variable. And if it is, then what is this H, which is yesterday already Camila mentioned as kind of 1/3 in some R to the H mean R in the power H. H is an exponent. Okay, so there are different questions that I may ask about this probability distribution, and I probably need to focus in this direction. And what we discovered, first of all, this empirical fact that the how much you need to burn fuel to drive your car is practically independent on the viscosity of the air. It's the same on the winter and in summer, etc. And this is something which physicists explain very loosely using the idea of a cascade. And this is the following idea. It tells you drive the car, it pushes air on this scale of a car, or you try to pump through a pipe. So you just push it on this scale. But what you create many different vortices. And on your large scale on which you drive your car, the Reynolds number is huge. When you drive your car, it's 10 to 6. Okay, so you leave behind a big vortex for which viscosity plays practically no role. It's almost ideal fluid on this scale, but this vortex breaks and gives its energy to smaller vortices, and this vortices breaks and gives its energy to smaller vortices, and then eventually it goes to such a tiny vortices for which already their product of their velocity times their scale would be 0.15 centimeters per second, which is the viscosity of the air. This idea, which almost 100 years ago was conceived by Richardson and then kind of invented by Kolmogorov, and then one can say, okay, just loosely speaking, in a moment I'll derive the equation. So if you say that I take this delta V on a scale R, if I take it squared, and my density is unity, as yesterday, so it's more or less an energy, a kinetic energy of a velocity of a vortices of a given scale. If I divide it by a typical time, which in fluid mechanics is always distance divided by velocity, so that would be energy per time. That would be energy rate with which I pump energy. It will be the same rate if it's a steady state turbulence with which I burn energy. So a cascade tells you this must be the rate with which energy passes through a given scale. This rate must be the same if I pump there, the same as I dissipate there, and it must pass through every point. That explains this empirical fact that we need to.
Wait, you just seem to have mixed the idea of different points in space with the different.
I'm now speaking in Fourier space or in scales. So what I'm saying that.
You are or not?
Yeah, I'm now speaking in scales,
Okay.
not in space, but in Fourier space, if you wish. So we put energy in big vortices, we dissipate energy by small vortices. Every intermediate scale must pass this amount of energy, and it suggests
Why
you.
doesn't it jump? How do
a good question. Why does not it jump? And that's precisely what Nati talked about, namely, could you have infrared directly talking to ultraviolet? That actually can happen in a compressible flow when you create a big perturbation of compressible gas and it breaks into a shock. And it burns all your energy on the shock front, which is practically molecular scale, right? That could happen. But we're talking in compressible fluid, and it took like several decades for people to really make sure that it's kind of a local in scales interaction, okay? But it's a legitimate question, and there are cases of non-local turbulence, namely where the infrared directly interacts with you. But you see that there is a more subtle non-locality here. It's just on the next level. Okay, so at this point we say that it suggests a scaling. It tells us that delta V cubed divided by R must be like this. So if there is a scale invariance, it tells me that delta V must scale as R in the power of 1/3. And then Kolmogorov came, as it was kind of a hand-waving type of argument. Then Kolmogorov came.
So when was that known, the 1/3, or who claimed that first?
The first was Richardson, 1926. From a very, very phenomenological arguments, which I don't want. With balloons, yeah. There was actually a Lagrangian flow. He thought how two balloons separate and found out that it's super diffusion, that R squared grows like T cube. And then R squared divided by T cube exactly has dimensionality of epsilon, of energy burn rate per. Anyway, Kolmogorov derives this equation. He just took Navier-Stokes equation. No, delta V is dimensional. Yeah, everything is dimensional except Reynolds number, you know. So what Kolmogorov did, he took Navier-Stokes equation, at one point multiplied by velocity, and the other point derives the equation on the second moment, assume it's a steady state, and just derived it. This is a third moment of velocity difference, proportional to the energy dissipation rate times distance between points. And even factor you can derive, find in the textbook, okay? So it could be in 2D, in 3D, in any dimensions, the scaling is the same, and it immediately suggested that you must really have, and then with Sasha Zamolodchikov, we actually derived a more, also third order, but 3-point manifestation of this cascade. So in a sense, the fact that you really, your energy goes from large scale to small scales, it has consequences on this level of the third velocity moment, because your energy is a second velocity moment. Your energy is V squared, so energy flux is V cube. So in a sense, it's opposite to what Nati talked before the lunch, is that we pose the question in large scale, that we have a force system, and we look for the answer in small scales, what actually happened along this cascade. And what we find that indeed it is this 1/3 scaling, it's beautifully supported by measurement, and for a long time we all used to say that there is the only exact result in turbulence theory, and this is this law. So then we return back to our assumption about scale invariance, and we ask, okay, if delta V cube is R, then this H must be 1/3. And that's precisely these beautiful theorems which Skrihidi and Delilis and other people proved recently, and that was Anzager conjecture, that if our H is larger than 1/3, you cannot have energy dissipation, because you cannot have this cascade. Your delta V cube must scale like R, so that you bring all your energy to small scales. So you cannot have a dissipation rate going finite when viscosity goes to 0 if your Hölder exponent is larger than 1/3. It's really important thing. This is why it took so many years, but now we're totally happy that we have it. So for us, the fact that the dissipation rate does not depend on viscosity means that as you decrease viscosity, you just increase your cascade. It's getting longer and longer and longer, going to smaller and smaller scales. But it carries the same amount of energy and eventually burns it no matter at what scale.
So I've heard Sager stated in terms of 1/3 Hölder continuity, and that's because your rod was, which is about how it depends on R, which is the length.
Exactly, but this is, you know, delta V cube is proportional to R is essentially a statement that this is your Hölder exponent, at least for the third moment, it's 1.
So that's where the,
yeah, okay. And this is a boundary between burning energy, so if your H is less than 1/3, you can burn an energy. If it's larger, that's Anzager conjecture. If it's larger than 1/3, forget it. You cannot have a constant flux over scales, so when your viscosity would go to 0, your dissipation rate would go to 0. Okay? Yeah. So you want energy dissipation rate to be independent on viscosity, you need to have a constant flux over scales. That's a statement. Okay, then we say if it's 1/3, then let's return to this question about scale invariance. Can we indeed now prevent? This would be a huge, any self-similarity is a gift for any engineer or physicist because you don't need to measure function of two variables. It's very expensive, right? It's like similarity what Reynolds invented. You can just take a small model of a ship, put it into your wind tunnel or your aircraft and just measure everything on this scale. You don't need to build this whole thing. So we really very much want self-similarity. It's a very practical nature. And it's not here, unfortunately. So when we go and measure these exponents over here, and we would expect them to be n/3, if this would be true with h equal 1/3, we find that this is not the case. And in particularly, let me return back, this is what a difference between exponents that we measure and n/3, which would we expect from self-similarity. You see that when on the third moment it is 0, so Kolmogorov is right. The third moment has the Gölder exponent of 1/3. The third moment scales like r in the first power. All the higher moments scale with larger Gölder exponent. All the smaller moment has a smaller Gölder exponent than 1/3. So my field, statistically speaking, is more rough.
That line is minus 1.
No, this is already difference. This is difference minus n/3. So for n equal to 3, it is 0. And then here it is larger, which means that if I would measure only second moment, only spectra, I would think that my field is more smooth than it is. If I measure only high moments, I would see very, very non-smooth configurations. What I personally believe that when space dimensionality goes to infinity, then you can see almost shocks, even though it's incompressible fluid. But at larger dimensionality, you're closer and closer to a shock, which is just a jump in velocity. And this essentially is a challenge. This is the first challenge that we have, is how to explain all those numbers, zeta n's. The third number is clear what it is. It's unity, it's a cascade. But what is the fourth number, the second number? Even the second number, which is not 2/3, if you Fourier transform it, it will be k minus 5/3. And this everybody thinks that Kolmogorov proved the spectrum of turbulence is k minus 5/3, and it's not. We measure the difference. It's noticeable, right? It's probably the most kind of well-known incorrect result about turbulence. The spectrum is not 5/3. And so this is, and so I briefly tell how we at least started to develop a language on which we try to understand it. And it again goes to what Camilla told about. Let's consider a simpler problem first, the problem of a transport. So let's just take and just look how particle moves. And if we look how particle moves, then we may ask the following question. If, let's say, I know that a distance between any particle scales like some power. For particular case of incompressible turbulence in 3D, it would scale like A would be 3, but generally some power. And then I take several particles, because when I consider multi-point configuration, high moments, I consider several particles. And I may ask, are there some function which do not grow like this? Namely, if this would scale like this, a generic function would grow like time in this power, right? Because r² grows like this. If this is scale, is uniform with this degree of uniformity, but some of them aren't. And those are things which we would call martingales. They do not grow as we would expect. And even some of them, one can find that martingales, they do not grow at all. And it's easy to make it just for usual diffusion. What happens with turbulence is that our diffusion is not a usual diffusion. It's a diffusion in a non-smooth velocity field. Already third moment has this Hölder exponent, which is 1/3. So we definitely non-Lipschitz. It's definitely, well, statistically at least, we are not Lipschitz, which means that there's no uniqueness of trajectory in the turbulent field. And so what we really find out that there are very non-trivial conservation laws for which you can build out of statistical geometry. So when you take multi-particle configuration, you can take such a function of angles or shapes and such function of distances so that your growth of distances with time is compensated by the decay of shape fluctuation, because with time any shape fluctuation turn to isotropic, so you forget your shape, right, what you initially had. And now I'm thinking maybe, yeah, no, that's okay. So, and now you can explain those anomalous scaling on this length. This is explanation. It's not a derivation, not a proof. This is just, I think that physicists started to conceptually feel something, but definitely unable to prove anything. And the statement is like this. Imagine that I would like to build a conservation law, again, on martingale, Lagrangian, out of velocity difference squared. This is a square of velocity difference, longitudinal, between two fluid particles. That's the distance between two fluid particles. That's the initial distance. This all is a function of time. As my time progresses, it would go into something like this. So I'm asking, can I find such function f so that this would not be growing? So the growth of distances r, they on average grow, any positive power of distance growth, would be compensated by the decrease of this because two particles decorrelate. The velocity is less and less correlated as they go away. And then one may argue as following. So u squared
Is increasing.
Well, u squared, if you measure the velocity difference, is increasing, and r squared is increasing, but they're different laws, and generally dependent on space dimensionality. Now something, you remember the cascade scaling did not depend on space dimensionality. Now it's about geometry. It's about how two velocity vectors decorrelate, and it's also about how distance grows. So if you take it at t equal to 0, this is just a second moment which is governed by this exponent, which is zeta 2, which is not too short, I remind you, right? Which nobody able to compute. So now, if you go to large time and you say that you assume that when time goes to infinity, this distances ratio of my distance at some t are not, which contribute this average. Of course, there are different realizations. But I'm computing some specific average, and I assume that the main contribution would give such configuration when this goes to infinity. Then I again suggest that it forgets its initial distance. To forget its initial distance, this function f must scale with precisely this scaling. So when I interpret now, what is this strange scaling, xi2, this is xi2, not zeta2, which Kolmogorov expected to be 2/3, and which we now know is not equal to 2/3, the answer is, this is a scaling with which two velocity decorrelate as they grow. You can make it scaling in time, you can scaling as a function of distance. And it's something which depends on space dimensionality, first of all. And we don't know how to derive it, we just can measure it. At least we know how to interpret it. We interpret it in terms of this, what we call zero modes or statistical interval of motion. So that's more or less the kind of the language which we suggested that we so this is something that if there is any moral out of it, that by Noether's theorem we used to think, you have a conservation law, it gives you a symmetry. You have a symmetry, it gives you a conservation law. If you're Hamiltonian, and this is a Hamiltonian system in the limit of viscosity going to 0. But in our case, it's different. This extra conservation laws, which is a stochastic geometry in a sense, they give us all this scaling exponent, which essentially tells us the following thing. The higher moments you look at, the more rare fluctuation you look at, the more and more rough your velocity field looks. Your Hölder exponent is getting lower and lower in roll. It deviates.
More and more random?
It looks more non-smooth.
Oh,
Your third moment has a scaling 1/3. Your second moment has a scaling a little bit larger than 2/3. It's a bit more smooth than you would expect for Hölder 1/3. But your 16th moment have a scaling which is much, much different from 16/3. It's much more rough, okay? So in a sense, this turbulent flow is a set of very different realizations with different degree of smoothness. And the respective exponents of moments are the respective scalings of conservation laws. And different conservation law corresponds to different geometries. The higher you go, the more fluid particle you need to take, the more complicated geometry you can build out of it. And so, and that what breaks the scale invariance. And again, the set of numbers nobody was able to compute, to derive, to. I believe that when d goes to infinity, it saturates into a constant. But again, I was unable to prove it. And yeah.
That's not a realistic thought, though, right?
Huh? Oh, we have now numerics.
The dimension does not go to infinity, does it? Oh, for numerics.
Just, you know, give people a little bit more time. We now have 6-dimensional numerics, pretty good Japanese, and they show more or less what I expect. I mean, there's nothing wrong with moving fluid in 6 dimensions, but I want like 26, and that would probably take 100 years. If you want turbulence in 26. But as I said, it all depends on space dimensionality, and 2 is very, very special, as always. And in particularly in 2 dimensions, when you look at your Euler equation without viscosity, it has this kind of very nice Hamiltonian form. You can introduce vorticity, which is now a scalar, a pseudo-scalar. And so you can write it in this form, which means that the vorticity is a Lagrangian invariant. Any function of vorticity is conserved by the flow. It's incompressible fluid. So in particularly, it means that now you have 2 quadratic invariants. And from now on, I really want to have many fluid mechanics because 2D, particularly because of geophysics, allows many relations between a stream function of a velocity. Velocity in 2D could be, because it's incompressible flow, I can introduce a stream function, and then my stream function is related by this scalar field, which is transported by it. It's just a relation which has a single parameter, m, and it runs in a family. For Euler equation, m equal to 2, but there are many other models. You can have a rotating fluid in which you will have one relation. You can have a homogeneously heated fluid. So it's very interesting and important to have the whole family. And in 2D, we have the whole family of fluid mechanics. And now they all have the same property. They all conserve any function of A because it's Lagrangian invariant. But they also have a Hamiltonian, which is quadratic. In this particular case, it's just psi times A. In the Euler equation, it's V squared, which is again psi times omega. And so now that you have 2 quadratic invariants, it's, by the way, this Arnold noticed that this is, they all belong to this, they all describe geodesics. This Euler equation for fluid is the same, just infinite dimensional version of Euler equation for solid body. Right? It's incompressible fluid. What it can do, it just move perpendicular to itself because it's incompressible, right? So it's Euler equation for a solid body. It's a finite dimensional version of Euler equation for infinite fluid. So you can, all this family of models could be presented as some geodesics. But I want to go a little bit faster because this type of system has now not only cascade of energy towards small scales, but because it has 2 quadratic invariants. For example, for Euler equation, you have V squared, which is energy, and omega squared. Because any function of omega is conserved, omega squared is conserved too. So now that you have 2 quadratic invariants, they cannot be pumped at one scale and then flow to some small scale and both be burned at this scale. Because if you burn a finite amount of V squared, you burn an infinite amount of omega squared at small scales because it's a derivative of V, right? So if you go to very, very small scales, for a given velocity, you have a lot of vorticity. And this type of argument suggests you that if you have 2 quadratic invariants and they scale differently with a wave number or with the derivative, then they must go different ways. One of them would go towards small scales, what we call direct cascade, and another would go to inverse, in inverse cascade to large scales. And that was, Ansager had this, again, as many things that Ansager did. Ansager actually almost did passive scalar. This much later, Gregory went to this basement at Yale, and they found handwritten notes of Ansager, where he almost came to this equation for passive scalar, which we solved in 1993. In particular, Ansager has this idea of inverse cascade, but not as a cascade, but he had this idea that there must be, the vortices of the same sign must clump together and produce big vortices. This is kind of proto-inverse cascade idea, but the idea itself was suggested by Krajkman and Zakharov, and it's now I want to talk about this inverse cascade. So imagine that we produce, yes?
Wondering, is there any effect, even odd dimension, in terms of this inverse cascade? So I'm just asking because there was this intriguing talk by Falkovich where he suggested a connection between anomalies and turbulence, and it's known that anomalies are kind of different in even odd dimension.
That's true. But, well, we do have anomalies. I mean, first anomaly in physics was fluid mechanical, not axial. For some time, it was erroneously thought that at every even dimension, you would have inverse cascade because you can introduce higher analogs of vorticity, some kind of way. But no, then we can prove, and we actually did it, that you don't have a quadratic invariant in higher dimension. So your fluid mechanics is very different even in odd dimensions, but any dimension different from 2, you have only direct cascade.
Is it a numerical exercise or is it?
Yeah, we have numerics for 3, 4, 5, 6 dimension. Yeah, that's in a sense. But on the other hand, it's just you don't have a quadratic invariant. Because what produces inverse cascade is just you need a second quadratic invariant. But the nature of anomaly is really different. But then again, inverse cascade, as you will see in a moment, doesn't have this anomaly. It has something much more interesting. Okay, so inverse cascade. So now what I want to talk is what happens when you pump system at small scales and it's getting towards larger and large scales. It's totally bizarre if you think about it. It's kind of self-organization because we would expect turbulence to fragment things. It's okay that you drive your car, you produce big vortices, and then you wait for a while and you see all these small, vortices which eventually dissipate into heat. But imagine, and that's what happens, by the way, on our planet, and particularly on big planets like Jupiter, you produce small-scale vortices, give it some time, and they produce bigger and bigger vortices. That's kind of a self-organization. It's still turbulence, a random system. Yeah? And it's very interesting now to ask all these questions that we asked before about direct cascade, to ask them about inverse cascade. So now we have this kind of a double cascade picture. So we assume that we pump system at some intermediate wave number, and then we have this direct cascade, and then we have this inverse cascade, and we'll be mostly talking about this inverse cascade. It's again a random field, etc. Now one can, again, because we have a different models with different m, and m could be even negative. For example, this is what is your Charny-Hasegawa-Mima model. It's a very fast rotating fluid or very magnetized plasma. In this case, this relation between stream function and Lagrangian invariant, it's even negative. So you can have this, this is called sort of stream function. Let me return to this point, is something curl of which gives you a velocity. So if you have a velocity in 2D, and its divergence is 0 because it's incompressible flow, you can introduce a stream function scalar psi, which is pseudoscalar, of which two components of V presented like this. So again, incompressibility allows you to replace a vector field V by a scalar field psi. Okay.
Flow lines that V go along.
Yeah, tangential lines to streamlines are the lines of constant stream function. Okay. And so now what I want to do, I want to just look, and so here what is these rounds are scaling exponents of my scalar Lagrangian invariant, which is vorticity for Euler equation. These are scalar exponents of stream function. So just by power counting of the same type as we did for, again, for example, for Navier-Stokes here is m equal to 2, and you see a 2/3, which would be A is for Euler, that would be vorticity, is something which is transported by the flow. So A is my Lagrangian invariant which satisfies this equation. So without forcing and dissipation, this would be just invariant. It would be a tracer, just goes in. Okay, okay, good. So here we've got the scaling exponents. Again, this energy cascade scaling, it is this 2/3, which is for stream function, and for 4/3, no, for this and for vorticity is minus 2/3. And then again, we ask the same question. So the third moment would be the flux. What would be the scalings of other moments? And we find, much to our delight, that now the probability distribution of velocity difference at a given scale is scale invariant. What? Scale invariant. So it's self-similar. So if I look, for example, at the probability of vorticity at a scale r times r in the power 2/3, that would be two-dimensional energy cascade. In 3D, energy cascade is anomalous. There is no self-similar probability distribution. In 2 dimensions, it is self-similar. You see there's for different scales. F is a very ugly function which nobody can compute. But it's a single function. You see, for different r's, you don't see the difference between, there's all curves collapse. Okay? This is for Euler, this is for surface quasi-geostrophic. So what is the statement is that for different scales, this is a function which we cannot compute. We don't know what is this function. But we know it's a function of a single argument. It's not a function of omega at r and r separately. It's a function of omega divided by r. So it's self-similar. Okay? Again, it means that all these fancy martingales, all this stochastic geometry, which gives us the anomalous scalings in 3 and higher dimensions, is dead in 2D. Is dead. There is no separate scalings for higher moment. There must be some very powerful, again, I spent many years trying to somehow prove it, that in 2D you just cannot have anything but Kolmogorov scaling. Any multi-particle configuration, you cannot build a integral of motion which has a different scaling than what Kolmogorov suggests. I failed. This task for mathematician. But empirical fact is as following: there are no anomalous scaling. There are no such non-trivial, at least they have a scaling which is not leading in this order. It's a self-similar distribution. And then we're getting greedy. So we say, okay, if it's scale invariant, maybe it's even conformal invariant. Because in a sense we say, okay, imagine that I make turbulence in some domain. There is some small scale forcing, really like my lattice spacing, it's my forcing scale. I'm now in inverse cascade. And then I have another domain with the same forcing at small scale. And of course, by Riemann theorem, I have a map of this domain to that domain. Is that map also true for multi-point statistics? So if I just take in this domain some, I don't know, a joint probability of vorticity being here, here, and here, such, could I just map it by this map into this domain? And so this was a question, and for a while the general answer was not known. But after a while, and again, it's not something final, but we found a triple moment of vorticity. This is still unpublished result, which shows that this triple moment of vorticity is non-zero and it is not a conformal invariant object. So in a sense, what we can say is that if you are interested in the bulk statistics, in multi-point statistics of, let's say, vorticity field, it's not conformal invariant. It's not conformal invariant. There is, Polyakov tried for pretty long, he's still trying in a sense, last time we've met, to build some kind of a generalization of conformal field series that can give you a certain moment of pseudoscalar, not yet. But what? It's everything 2D now. Everything 2D, everything is inverse cascade. Okay? So in a sense, at the moment, we can guarantee that at least we measured a one non-trivial correlation function, which definitely is not conformal invariant, but we do found something which is conformally invariant. And it's something which is very, very practical. If you think about a planet, for example, this is our planet, right? So this is, you have a lines, which is a lines of between vortex, which means cyclone, which means in the same, in the opposite direction to the Earth's rotation. It means that it has negative vorticity. Or you have anticyclone, in which your fluid locally rotates in the same direction as you have a rotation of the planet, and boundary between these lines is usually something where weather changes. We're very much interested in the boundary between cyclones and anticyclones, because a cyclone is usually raining and anticyclone is usually local high pressure, because when you rotate fluid like this, you create a high in the atmosphere. When you create it opposite direction, you create a low. So these are very interesting lines, and these lines of zero vorticity we found to be conformally invariant. And that was a big surprise. Well, okay, yeah. And
So the atmosphere is thin enough that you can model it with the 2D theory?
Depends on the scales. Atmosphere, I mean, troposphere, which you're interested in, is 10 kilometers. So the moment you speak about, 50-kilometer scale and all the way to 10,000 kilometers, you're more or less two-dimensional. It's a lot of phenomena which you do not account, but the pumping is generally at small scales. All the convection, all these things, they work on scales like 10 kilometers, 20 kilometers. So the moment you're at 100-kilometer scale, that's inverse cascade. Not very long, Jupiter is better, but still kind of decent. Now, that's already numerics. This is a picture of vorticity. And every color is just a single connected cluster of positive vorticity. All negative vorticity is black. Here is much black as colors. It's just your eye fool you, right? First of all, it shows you the state-of-the-art numerics. So this is really, this is this is a forcing scale, more or less, right? So this is really a big interval of scales. You see how fractal is this field. So now what we'll be doing, we'll be studying this. Now this red line is a zero vorticity line. It's not a simple line. It returns and touches to itself. So you can define it's a blue kind of a hull, an envelope of this line, which is without self-intersection. So every time it has self-intersection, you don't go in. You just continue on the external perimeter. And blue are green are double points. They also fractal. They not have zero measure. You see they kind of cluster over here. And then you can see what are actually their fractal dimensions.
Blue is what?
The blue is external envelope. Red is a zero vorticity line as it is, just measured, okay? And it's not a simple curve. Blue is a simple curve. It's external envelope, and green are double points, which is essentially different. And then you just look at their fractal dimension, and you see 7/4, 4/3, and 3/4. And this is something which rings a bell, because it brings us to, first of all, to critical percolation. And the critical percolation is a type of a phase transition when you have a random landscape and you start filling it by water. So when your water level raises, at some point, you're passing a critical state. It is as probable to sail from one end to another as to walk on a shore, and it has kind of similar scaling. But more important, it brings us to SLE, which here are people who know this thing much better than me. But it's a language, and this is a really language, which is a mathematical language, which I did not know about when we were starting to study all this. And it's a very beautiful language invented by Löwner 100 years ago, probably already. And this is the following thing. So if you consider half plane and you consider a curve in a half plane, so tau is just a parameter along the curve. So you can always map this half plane minus the curve into just half map. In a sense that you can absorb this curve into the boundary, which is this boundary. And then, of course, the tip would be absorbed into some point over here. So this map is kind of give you this point. As your curve continue to move, this will be a function of time. This map would change as your curve would move, but it will correspond to this point, which is an image of a tip moving along the line. So the idea of Löwner was that you can encode a shape of a curve on a surface by a motion of a point on a line. It's a very, very beautiful idea, and using Riemann mapping theorem, yeah, which is essentially just a straightforward use. And then if you, it's a very deep result, and it's beautiful. I mean, I just, at the moment, particularly, yeah. Now, where is this? Where is toxic energy? Wait. So, if you also define it at infinity, it must be close to the unity transformation. So you define kind of, you normalize it by requiring that the next term 1 over z would have this form, and it immediately gives you a Löwner equation. So this equation tells you that this mapping G is completely defined by this motion of z of t. It's called driving function. Okay, so for any law which you prescribe, you can solve this equation, and it would give you this map, which essentially gives you the form of this shape. So that's called Löwner evolution. And then 80 years later, Adel Schramm, also at the time at Weizmann Institute, we actually at the same time started to work there, just Nati left, and we came. Let's take this driving function, just a one-dimensional random walk, Brownian walk, okay? And then now, because everything is dimensionless here, that it's determined by a single number, which is essentially how fast it diffuses. Again, it's a diffusion along the line, and it has this number, it's a dimensionless number. And you can prove that if k is less than 4, then it's not very, much wiggling your curve does, and it's a simple curve. The moment your kappa is larger than point is moving on a straight line. Yeah, in a sense, the only thing, is just a diffusivity. Shape is encoded in this equation, but as long as this is something which is, it's just determined by its diffusivity. And this diffusivity is dimensionless number, and more or less you are in this interval, because when kappa is larger than 8, at least, well, there are some exotic physical models, but we aren't having it here.
And then the next picture has shape as a whole, right?
No. This thing is when your kappa. The middle one tells you that it's not a simple curve. When kappa is larger than 4, the curve returns to itself. So then what you can define the hull. You can say that points which are invisible from infinity, you disregard. So instead, you'll be making a map of outside of this region. That's what this G would be. The G would map a hull, which is outside, which is visible from infinity. Okay. Now, what was the black one is kappa is larger than 8, which is not, I won't consider. This is, it means that now you start feeling just regions, kind of. So its measure is now full measure. Yes. Okay. But what was also interesting is that there is a certain duality. So if you look at your curve, and it's not a simple curve, then it always has this envelope outside, which is a simple curve, and they have a certain duality between them. One corresponds to kappa, which is larger than 4, another corresponds to kappa, which is less than 4, and then their dimensionality, which is related to kappa, is in some kind of a dual relation, and in particularly, there is this dual pair, which is 7 over 4 and 4 over 3, which exactly what we found for earlier equation in inverse energy cascade of two-dimensional turbulence. Okay? And then we went and we just did what we call a Schramm test. We just took let me just show it, because it's a totally heroic effort of Antonio Celani and Guido Buffetta. So we took this line and we built a driving function for it. Namely, we just brought it into small pieces and made a Riemann map out of it. And so we just computed numerically a driving function. And we've shown that it's a Brownian walk. And we found kappa. And we found that kappa corresponds exactly to what you would get. So this is the xi squared. You see that it's xi squared linearly growing. So your kappa is the slope of this curve. You see that its statistic is Gaussian. And you can also check independently that this is really independent increments. This is a true Brownian walk, which you find here. And here you divide xi squared over t, and you have 6, kappa equal to 6, what you expect. Now this pink is even more interesting, is that we took our vorticity field, which remember was a scale invariant. It has this Kolmogorov scaling, exactly like Kolmogorov predicted. And we made a Gaussian field out of it with the same second moment. So we keep a spectrum of turbulence, but destroyed all the cumulants. It immediately lost this property of isoline being SLE. It immediately lost the property that isolines of this field are Schreiman-Loevner evolution. So it is something in these higher correlations of vorticity in different points, really in cumulants, which determines that the isoline would exactly be, this conformally invariant SLE curve. If you replace your field by a Gaussian field with the same second moment, it does not work. So you destroy all these things. This is something for which I don't have even physical intuition, not speaking of understanding. Then, of course, we went to this whole family of models, and we started checking it, how it works for other moments. And again, you see that more or less it's everywhere you can find this property. Again, it's an inverse cascade. Another alternative way of looking at it, you can take this isoline and make a tangential vector to it. It's fractal line. Mathematically speaking, this is object which does not exist. But of course, for physicists, everything is smoothed on a force scale. It's my inverse cascade. I have a finite scale of forcing, and this is the width of any line. My line could not be, seen as in this. So I can define a proper procedure in which there is a smoothing, and so I can take this vector and ask if this angle has a Gaussian statistics. Because for SLE curve, the angle would have a Gaussian statistics, and I also can read kappa from the statistics, and we check that it really has a Gaussian statistics here. So more or less, we did it for different things. Then we even, now you remember this was a scaling of my vorticity at different m's. This is my family of models. So I have my stream function scaling, I have and this is my kappa. So it's a very non-trivial function of m. And I don't think it's really, would be probably too much detail here to go. So we have, I think, a physical explanation which tells us why you have this transition at m equal to unity, because if you look at the velocity scaling as a function of L, it scales like this. So when m is larger than unity, it makes sense. It tells you that it's Hölder exponent, which is positive. But when m is getting less than unity, it's Hölder exponent, which your scaling would suggest it's negative, which means that essentially your motion of fluid particle is ballistic, and that's why you see this phase transition. Now, what we did was an inverse cascade. If we try to do, this is an inverse cascade for 2D. If you try to do it in a direct cascade in 2D, nothing like this. This is property which works only in the inverse cascade. In the direct cascade, the curve is a multifractal curve. It does not have any self-similarity. Not speaking about conformal invariance, you can have different moments, you have different dimensionalities. So the scaling, the direct cascade seem to be not self-similar. And it makes sense because you have it's a direct cascade. It means that you measure something on a scale much less than your forcing scale. Your forcing scale imposes correlation between different points. You're trying to go down, but you're still within this big coherent forcing. When you're in an inverse cascade, you go to larger and larger scale and your forcing is small. You kind of effectively self-average. But again, this is a physical intuition. It's not something which anybody was able to show with any. Now, SLE is by itself is a very.
I was going to say, the thing looks like a map.
Huh?
On the left.
Yeah. So in a sense of, but of course, I mean, the idea of fractal was brought out of studying maps. How actually the shoreline of Britain, increases when you increase the resolution of your map. And then again, you may ask, what are shorelines, for example, of continents, of islands? Do they belong to this SLE class? So now, anytime I have any curve, I first check if it belongs to this class. But then you get a lot of information for free. There are a lot of statistics that's just simple hypergeometrical functions that you can compute. It's really beautiful. So there is a kind of incomplete list of what system producing this SLE. There are two types of coastlines, by the way, like sandy coastlines and rocky coastlines. It's only rocky coastlines, for unknown to me reasons, that produce this type of curves. And so I have last minute, so let me finish with the conclusion that, of course, turbulence is a way to dissipate, which means that it breaks time reversibility. It is an anomaly in a sense that even though this time reversibility is broken by viscosity, the effect stays finite when viscosity goes to zero. And our way of understanding it, the physical way of understanding, is a cascade. But fortunately, now mathematicians build these classes of solution totally unphysical. Fluid does not flow this way, in which Skerihidi and Delilis and other people build their solution, but at least those solutions dissipate finite dissipation in the limit of zero viscosity. Scale invariance is broken in all direct cascades. And inverse cascades seem to be scale invariant, and nobody was able to prove it or argue in any convincing way that it is so. And the whole statistics of inverse cascade is not scale invariant, but lines seem to be conformal invariant. So the lines really belong to this class, which is called SLE. And that's more or less kind of these two things which I think mathematicians should know. That we have these gifts with which you don't know what to do. These broken symmetries in a direct cascade and emerging symmetries in the inverse cascade. That's our Pandora gifts.
First line is true in 3D also.
The first lines is true for any direct cascade. In 2D, in 3D, in any direct cascade is kind of, if you look at the time reversibility, in the inverse cascade is also true. You have a third moment which is non-zero. It means that your time reversibility is broken for any turbulence. Okay? Even though you may formally consider inverse cascade without viscosity. It goes to larger and larger scales, viscosity is getting more and more irrelevant. But third moment is there, and it breaks time reversibility.
The reverse cascade doesn't exist in 3D.
Neither in 4D.
Questions?
Can you repeat the thing you said about coastlines and?
Coastlines are of two types, rocky coastlines and kind of more sandy coastlines.
Which ones are in the?
And SLE are rocky coastlines.
They're rocky. And
They have different fractal dimensions.
and they fit with the SLE theory.
Yeah. On probably some interval of scales, not like, because it depends on what scale you look. But in
You
a
look at a map of the Earth, and a Riemann mapping theorem is involved in the structure.
yeah, exactly.
Actually, that's why I became a mathematician. I was a chemical engineer, and in the second year, the calculus course was teaching us, and the guy wrote the kidney-shaped thing, and he said we knew about f of z and f prime of z, and he said you could move this kidney-shaped thing over to the round thing by a unique f of z, essentially. I thought, what? Not a formula.
Riemann got you.
Which makes on that. Sorry.
Did you mention this last line? Was there, I mean, sorry. Inverse cascades leading to symmetry was in your talk, it seemed like, but why do you think they may eventually break it?
Because if you don't have, you see, when you go to large scales, your viscosity is getting more and more irrelevant, right? So you need to dissipate. It's a cascade. It brings energy to larger and larger scale. So in any finite system, for example, your own Earth, right? It's finite.
Larger and larger.
You create at some point large scale flow, which is fed by this inverse cascade, which we call condensate. You may say that kind of, and it then breaks all the symmetries because it's now produces something which is, global scale flow. It's usually not global, but, and it stops early. It depends on surface friction, but it's eventually, but I did not talk about it because this was just a more general conclusion.